Good morning, Adam. So here is question one. Um, so here is the function. I just called the function now with the different parameters and s. So this gives us this should give us s the sign. So this is the signal, the sine signal in time domain, and this is its Fourier transform. This is a sine signal of 50 hertz frequency from here. So this is a 50 hertz frequency. So we can also call this function for C, which is cos, and it should give us the cosine signal, and it's the same frequency, 50 hertz. We can also call this function for a different any other character here would give you the three combined signal and its Fourier transform. So we design I designed a signal which is this combined signal of different frequencies and different amplitudes. And by using a different character, we generate there is a combined signal, and here are the three different frequencies after doing the Fourier transform. So this is the application of Fourier transform. These three signals are buried into these three frequencies are buried into the signal. And so that is for the first question. And for the second question, we have a function that generates a square wave. It generates a square wave, and we're going to run it. So let's run it. So here is a square wave of width. You see that. Let's start with a width of 0.2, and when we run it, you see that the width of 0.2. You see that this is the Fourier transform. See how smooth, and it's not too steep. Let's go to 0.4. We'll see that this is the width of 0.4. It becomes steeper, you see. And if we go to 0.8, it becomes more steeper as the width increases. It becomes more steeper, and this becomes more flat now. And so that is the effect of increasing the width of the square pulse. Also, the gives when we run the signal, it shows us the Gibbs phenomenon by increasing the number of ends. We're able to get by increasing the number of ends from 5 to 50, so we're able to get a more flattened out square pulse here, which implies that this is the Gibbs phenomenon, this overshoot and undershoot. So this is because we cannot obtain an infinite amount of harmonics. So when we go to 1000 harmonics, we get a more flattened out curve. This is the Gibbs phenomenon. So question 5. For question 5, we have our signal. Here is the code, and here is the code. Here is its Fourier transform, and this is for HF. This is for LF, and we remove the DC component by removing the mean. So if we were to run this code, we would see that this is the magnitude response and the phase response of the filter that we designed using an appropriate cutoff frequency. Here is the signal for LFN, and here is Fourier transform, and also this is the signal for HFN, and this Fourier transform. We see that the significant frequency components, but as we move this way, it becomes noisy, which could be as a result of background noise. So that is it for question 5. And for question 6, we'll see that we have the different channels, the different signals from 4 different channels plotted. And if we were to run this, we would see that there's some background noise, could be as a result of background noise. And if we were to see this plot, we would see that here is the plot that I just showed. Here is the frequency, the Fourier transform and the frequency components, and there is the short-term Fourier transform as well. So we have that for question 6, and question 8 gives us the unit circle with the zeros and the poles, and that is it. Thank you.